it's been a while since I did a video, so I thought I would do a video. The thing I've really been wanting to make a video on lately is testing. And I think this is too much for one video, and so I'm going to start the testing, I guess it'll be a testing series with a very sort of like, just a nuts and bolts of like where to begin with testing. And so we're not even going to start with the whiteboard here, or maybe I'll do a little whiteboard later or something, but we're just going to start straight away with sort of things that you'll need and sort of how to get started. So, right. So I've got this old amplifier. I was actually cleaning out my garage, right? And I took this thing off the shelf and tossed it into the garbage can. And then I thought, I wonder if that thing still works. So this is a Radio Shack amplifier from about 25 years ago. It's a car amplifier, and Optimus brand, the XL-50, 50 meaning watts. It's supposed to be able to generate 50 watts. It's a stereo amplifier, and we're going to find out today. It looks like it does still work here, so we're going to find out how it performs, and we're going to use a couple of different sort of ways of testing it. And so the first thing with testing, I guess, is you need to generate a signal. All right, so you need a device that you want to test, in this case an amplifier. You need to generate your signal somehow. So I've got this really cheap sort of AliExpress signal gen here, and it works fine. You don't need one though. You can use a computer actually. So if you have a computer that has a sound card, you can generate a perfectly acceptable 1K signal or whatever. So that'll get you started with testing. Now, a computer is going to struggle to generate some things that we'll be looking at later, like square waves. But as far as generating just like a pure sine wave goes, any computer sound card will be perfectly fine for that. Ignore this. This is just the power supply. It's simulating the 12-volt battery from your car. So here's our device under test right here. This little thing, and then of course we have a test load here. And so when you're testing an amplifier that's supposed to drive a speaker, you need to test it into a load. You can't just plug your test equipment straight into the amplifier. It needs to be loaded down, or else it doesn't actually generate any power. And so something to remember when we're testing here is that power is volts squared divided by resistance. So because power is a volt amp, and so if you do the math with Ohm's law, if you're trying to solve for power and all you have to work with is your voltage and your load, you end up with volts squared over R. And so it's pretty easy. So in this case, we have a 4 ohm load, and we're developing, you can see over here, we're developing 2 volts RMS. And so you just do 2 times 2 divided by 4, and you can see that we're already set up here developing 1 watt at 1K, right? So this is our 1K sine wave. And that's really where you need to start. So with any sort of amplifier, you just sort of like got to get things set up so you can sort of be generating, you're generating whatever it takes your signal in to generate your 1 watt out. It's just a good starting place. So right away, obviously this is a very sort of a snapshot of what the amp can do. It's a single frequency, it's a pure sine wave. It's a single power level. Obviously a musical amplifier is going to be doing a lot more stuff, and so we're just getting the barest hint of whether or not the amplifier is working properly. But you got to start somewhere, and so that's where you start with these things. And so I have a load. You can see I've got 2 load resistors here. I've got a 4 and an 8, and I've got a little thing here where I can sort of test the circuit. I can clip in to the positive and negative leads here from the amplifier output. And I can also, I've got screw terminal block here, so I can flip this around and easily go between 4 and 8 ohms. And so we're going to do 4 ohms because I tried this earlier, and the amplifier, it's supposed to make 50 watts, which I presume is 25 watts per channel. But it wasn't doing anything, anything similar to that, driving 8 ohms, and so we're going to drive 4 ohms, which it seems perfectly happy to do. So we've got 4 ohms there. We've got we're generating our signal here. You can see the scope itself will give us what it thinks is the RMS and some other measurements here, the peak to peak and stuff like that. But it's nice to have an RMS meter, which is going to be accurate, much more accurate than this. You can see that as we scroll up and down with power here, every time I click through, it changes here, but it doesn't change at all here. See, so this is just much more finely tuned here. So we're just scroll down to, let's see if we can hit exactly 2 volts. And so I've measured these load resistors. They're really, really close, and so we can be pretty sure we're making about exactly 1 watt here. And so another thing to think about is that if you have a scope like this, inexpensive scope like this, they almost all have a feature where they have a built-in what's called a FFT. And so FFT stands for fast Fourier function, or I'm sorry, fast Fourier transform. And the Fourier transform is some math that you don't want to have to do yourself, but what it does is it looks at a wave and it divides it up into its various frequency components, right? And so a pure sine wave has a single frequency component. But anything that deviates from the pure sine wave can be described as multiple frequencies added or subtracted together. And so a Fourier transform will actually sort of spectrally analyze, it'll sort of chop up the wave into its constituent parts here. And so let's just have a real quick look at the FFT. And so the way I'm going to do that is called the math menu on this. So we'll go math, and it's way down here. So we're going to scroll on down. And all right, so you can see that it says 1K. Here's our fundamental frequency. I'm actually going to zoom a little bit like this. So now you see that we actually are looking at 2K here. We got our fundamental over here. And so the reason we want to look at 2K is that, generally speaking, the first bit of distortion that comes up in an amplifier is what's called second order. And when you're talking about orders of distortion, you're just talking about multiples of the fundamental. And so you would expect to see your second order at a 1K frequency at 2K, and your third order at 3K, and 4K, and so on and so forth. They're all just multiples of the fundamental frequency, is where your harmonic distortion usually comes in first. And so you can actually see, sure enough, creeping up here, it's very low, it's kind of creeping up to right there. And so these are 10 decibel increments. So we can do 10, 20, 30, 40. And so at 1 watt, our primary component looks like down here at our second order is down there, 40 decibels down, which is not nothing. A lot of amplifiers at 1 watt, you won't see anything. So we already are getting a hint at the sort of the quality of the amplifier or whatever. Also, have a look up here, peaking up about as much as our second order, even more sometimes. Let's see what that is up there. So we'll just scooch this over. See what this is over here. It'll be some multiple of the fundamental. Yeah, so that's 4K. So that's a fourth order. We already have a fourth order component here. That's about as high, or sometimes even higher than the second order. So that's also sort of an interesting sort of thing to note there. So let's scooch back here to where we were. All right, let's go back to our waveform here. We can see what we got. So that's a good place to start. Now, obviously this is just a single frequency, but let's just see what we can do with the frequency. And so the first thing let's do is let's see what the maximum power of the amplifier actually is, right? And so it's supposed to do 25 watts per channel. I have no idea if that is max or RMS or what, but we're about to discover that. So let's change our range here and start increasing the input power and see what we can do. And there we go. So what is that? We'll talk about that in a second, but let's avoid that for now. So before we get all the way up here into hard clipping here, right about here is where the amplifier, let's just get as far as we can before it starts doing that oscillation. And so it looks like we got 6.6 volts RMS out there. And so I'll get my calculator out. So it'll be, remember, our volts squared over R. So it's 6.6, shut up, times 6.6 equals divided by 4, which is our load. And so the amplifier is making 10 watts. Now it's one channel. I'll just be, I'll give it the principle of charity and assume that both channels would output 10 watts at the same time. It's more like 11. It's 10.89 or something like that. So what we really have here is a 10 watt per channel, or an 11 watt per channel amp before clipping, or actually what it does before it clips. Now this is interesting. What it does before it clips is it starts to oscillate. So have a look at that. So that is an oscillation. Let's zoom in on that and have a look at what the amp is doing here. Interesting, right? So that is not something you would probably actually hear. That's going to be up far above the audible range. In fact, let's find out. So this is another thing the FFT is good for. Let's go ahead and make sure that it's prominent so that we can, seems like it's most prominent, like right about there. And so we'll go over here and have a look. So this is where it is. What is this? So that's an oscillation that only happens near clipping at 315,000 cycles. So pretty interesting. I actually haven't seen a lot of amps that do that, but I mostly work with tube amps that I've designed. And so, but you would never see that. Like, let's say you were just testing, let's say you were just testing, that's too far. Testing down here. This is interesting. You'd also see some under sort of distortions sort of coming up here. That maybe as a result of that, oscillation. It's interesting. Like the noise floor, just generally speaking, is coming up. Interesting. So that's automatically sort of an issue. So it's not making power. It's about a 12 watt per channel amp or whatever, if we're being optimistic. It breaks into oscillation before it even clips. Now, give whoever designed this thing the benefit of the doubt. It hasn't been serviced in 25 years. The fact that it's still working, I guess, is pretty impressive. So there you have it. And we could increase our voltage in. We could actually probably increase it to 14 volts is probably the maximum that it would take before it, it started to die on us or something. And at that point, maybe it would make the 25 watts or whatever. But for now, let's go back down. We're going to try a different sort of test now. We're going to do a test for frequency response. I'm going to show you how to use a square wave to quickly test for frequency response characteristics of an amplifier. All right, so this is our 1 watt, well, it was a 1 watt sine wave, but this is a square wave. And you can also already see it, something interesting is happening here. So when you're testing with a square wave, it's always good to test the input and the output, because you want to make sure that you're not assigning to the amplifier something that's happening at the signal gen. So let's have a look. So here's what's going into the amplifier, right? And that looks textbook perfect. In fact, let's stay on this for a second so I can explain to you why it is the square wave would measure frequency response. The reason why a square wave is a good tool for measuring frequency response is that a square wave can be thought of as all frequencies combined together into a single wave. And so if you want to build a square wave from pure tones, you need very high frequency tones up here to fill in this area, and you need very low frequency tones down here to fill in this area. And so this leading edge of the square wave represents high frequency content. In fact, this is far above audio frequency range. A theoretically perfect square wave the leading edge of the square wave would be infinity frequency. Now that's not, in practice, that's not the case at all, because you can't have that. But it gets higher than the audible range for sure. And then down here at the very end of the square wave, depending on what square wave frequency you're using, it's basically DC down here, right? Now this is a 1K square wave. You can test with a 10K square wave to look only at the high frequency issues. But when you test with a 10K square wave, you're basically just chopping this up into 10 pieces, right? A 1K square wave, and just looking at the very edge. And so it's basically the same thing as zooming in. And so there's not a real difference between a 10K and a 1K square wave, except that you're just looking at the first tenth of the 1K square wave. And then you could do like a 100 hertz square wave, which would look only at the low frequency content down here. And so it's interesting, like in an amplifier that doesn't have a nice linear frequency response, that won't be square, the output. And what do you know? That's what we've got. So this is not square in a very particular way, and what this is called ringing. So I didn't actually expect to find this in this amplifier, although I don't have a lot of experience with solid-state amplification. But tube amplifiers do this all the time, and it's as a result. Now here what I'm doing, I'm just zooming in on that leading edge so we can get a better look at this ring. Tube amplifiers do this because of their transformers. Transformers are sort of big inductive devices, and they have a tendency to ring, and you have to do interesting compensation to get rid of the ringiness of transformers. But this is obviously a little solid-state amplifier, and so why it's doing that, I'm not exactly sure. But this is all, I'm just going to probably just go and guarantee that this is all happening outside of the audible range. This is probably all 20K plus, and so that's probably why the designer of this amplifier didn't bother to correct for that. It would have cost extra money to add extra components to correct this ringing, and they were just like, whatever, it's a car amplifier. And who in their right mind would test this with a square wave? Us, apparently. But you can see we instantly get some ringing there. But otherwise, the frequency response to the amplifier is commendably flat. And so in an amplifier that, for instance, had attenuated high frequencies, the leading edge of the square wave would be rounded off. And so you would know this amplifier is failing to reproduce those high frequencies. And in an amplifier that has trouble with low frequencies, this happens with tube amps quite a bit because they're transformer coupled outputs, and transformers are bandpass devices and they cannot amplify DC. Like this is a solid-state amp, it probably actually can amplify just DC. In fact, some solid-state amplifiers have the problem of just having DC on the output. That's not going to happen with a tube amplifier because tube amplifiers are kind of galvanically isolated at the output with a transformer. It cannot pass DC. And so what you see with tube amplifiers in a lot is that the square wave will begin to descend. It'll start up high up here and it'll be flat, and it'll kind of start to take a dive. And that is an indication that your amplifier is struggling to amplify low frequency content. That's what you see most of the time. If you're having an issue where the front is rounded off, that's an indication you're not amplifying high frequency content, and that could be some capacitive issues in your signal chain that you'd want to look for in that case. Keep in mind, the square wave doesn't tell you anything about distortion. So it only gives you sort of a rough idea of frequency response and allows you to tackle this ringing. Now, there are several ways of sort of attacking that ringing if you're designing an amplifier, but we're not designing an amplifier today. We're just sort of getting a ballpark for what it does. So we already know this amplifier has sort of a ringing problem. So we've got a couple things going on. It doesn't make power. It's got issues with ringing. But otherwise, the frequency response is pretty flat, so it's looking pretty good there. All right, so now let's see if we can figure out where in the frequency range our ringing is occurring. So let's go back to our sine wave. Let's go into the frequency area here. So this is back at our 1K. And let's start, let's see what we have here. We've got 2 volts, that's sort of our reference. and we know that our ringing is up high. So let's go right on up to a 20K square wave. So we're still making just about 2 volts, and so we haven't found our ringing yet. Let's go up, 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 50K, 60K. See, really, they probably shouldn't have even had the amplifier this high. They should have put a low pass filter in it. We're still at 2 volts, so here we go. So the ringing in this amplifier, you can see how, all right, we're at 2 volts still. We're at 140K, right? Now look, as we go up in frequency, our voltage is climbing. Oh my gosh. So we've discovered our ringing point here. The distortion is off the chart as well. Look at that. Let me get a little bit more fine-tuned here. We'll find the exact frequency it rings at. It rings at, or have we found our oscillation? We have to find our oscillation here. But it looks like we're ringing up here at 200 kilohertz. And also our distortion has gone crazy. Let's have a look at this distortion because that'll be interesting. All right. So we're amplifying the fundamental frequency of 209, and look up here. So 246, right? So this is third order. We got a big third order component here. And then what do we have over here? Yeah, then we got something up here to megahertz. Yeah, so pretty interesting stuff there. So that's a problem. So this could be actually easily solved. We could easily solve this by just adding a low pass filter. Sorry about this. Adding a low pass filter to the amplifier at the input to only allow, you know, let's say 30K and below. Really, you only need 20K and below. And so we could totally knock out this ringing and all of this distortion, the high frequency, and who knows, that might even knock out that oscillation that we saw earlier. All right, so let's go back down into the audio range here. Let's check out some other frequencies that are useful. So we're at 2 volts here. Let's go on up closer to the power rating of the or the power output that we've been able to attain from the amplifier here. We decided that it was something like that, I think. Let's go all the way up to 6.4 volts is what we think we can get out of this amplifier here. And so let's look at a few different frequencies. We know that this frequency, 1K, there we go, has a little bit of second, a little bit of fourth order up here as well, and a little bit of third there now too. And so actually near clipping, before it gets into that oscillation, up here at 10 watts or so, it's still a pretty low distortion. So this amplifier has got some good things going for it, but we're only testing at 1K here. So let's go back and try to see what we can do at some different frequencies. So some other good frequencies to test are obviously you go up to a 10K signal. Let's see what we got. And that looks pretty good. Let's see what the FFT has to show us. And that actually is excellent. Very nice 10K. Let's go up to 20K. That's the limit of human hearing. If you're my age, then your hearing is probably closer to 15 or 16K, and that is normal. We do have a little bit of distortion, but that distortion component is so far above the audible range that no one would ever hear it. So this actually looks really good up here. So now let's try to see how the low frequency distortion looks. This is where some amplifiers struggle, so we'll find out. So let's go back down. Let's start down here at 100 hertz. That looks good. In fact, we've gone up a little bit here on the scope reading, but actually over here, if you look on the multimeter, which is a better judge, you can see that we're about the same. So 7 volts again and 4 ohms, that's RMS. And let's have a look at the FFT. What do we want here? It's 100 hertz. Takes longer because there's less cycles for the thing to do the math on, for the scope to do the math on, so it takes longer for it to calculate down here. But you can see we've got 100 hertz here, we got 200 hertz here, and there's nothing. You know, we got, what do we have up here? The fourth again is kind of creeping up. But the distortion is impressively low here at 100 hertz. Let's go lower. All right. So let's do 40. So 40 is like where sort of the punchy depth of your sound comes in. It's a good frequency to test. Let's see. I'll give it a second here to do the math. It has to have a certain number of full cycles to do the calculation on. So any second here it's gonna let us know what it's got. Nice. And so it still looks really good at 40. Let's go right on down to 30. 30 is like deep bass. 30 is deep bass. It's like where sort of the fullness of your sound comes in. Give it a second here. That's the, sorry about the noise, that's the fan on my power supply kicking in. And still commendably low distortion at 30 hertz. Let's kick it on down to 20. And let's have a look at the wave just at 20 hertz to see what we got here. And so, let's see. You can see we've lost some power here though. This is interesting. So we were at 7-ish, right? So it's a 6.5, but now it's showing 5 here. So it's like, who do you believe, the scope or the multimeter? It's hard to say. So here we go. We can see it is getting smaller. So as we creep down here to 20 hertz, 19, 16, 15 hertz, we've lost a lot of our power here, right? And so let's go back up. Let's see where it sort of levels out at. .6. Where do we level out at here? We're still climbing. Still climbing at 45. And so this amplifier starts to lose power at about 40 hertz. Not a lot. It starts to lose power at 40 hertz, and as we go down to 30, you can see we've lost a little bit of our power here. And as we go down to 20, we've lost further power here, you can see. So, I mean, that's asking a lot, but honestly, most amplifiers can achieve 30 hertz with little or no attenuation of the output frequency. And so we didn't really see that on the square wave that much. But let's for instance, now that we know that we have a low frequency issue here, let's instead of doing a 1K square wave, let's look specifically at the low frequency issues with a 100 hertz square wave. So let's see what we got here. So we need to bring our power down because we're getting that oscillation in again. There we go. All right, so here is a 100 hertz square wave, and you can see that in the 100 hertz square wave, we do indeed have some low frequency attenuation there. And that's fine. If you were to see a 1K square wave that looked like this, it would be horrible low frequency attenuation. But in a 100 hertz square wave, this really isn't that bad. This is pretty typical and not bad at all. It's all right. So we're also doing it at a much higher power level than we were before. So we could do an apples to apples here. And let's see, go back to a sine and bring it down to the 1 watt again. That's where we're at before, 2 volts. And maybe it's the kind of low frequency attenuation that only happens at full power. So let's see now. And no, so it's just something that the amplifier has, generally speaking, which is it has a tendency to attenuate the low frequencies a little bit. That's fine. It's not so bad. Like, really, the frequency response of the amp is pretty good. And if you put a low pass filter in front of this, you could get rid of any of this ringing stuff, and probably you might even knock out that oscillation if you got rid of some of the high frequency on the input. Hard to say. It is a 25-year-old amplifier that is beyond its sort of shelf life. Anyway, so that's sort of basic testing. We've discovered some things about the amplifier. I'm going to do another video where we're actually going to get a computer out and we're going to run a program that will actually run sweeps, and it will give us the noise floor. It will give us all of the distortion across the entire frequency range. Yeah, it's going to do all of that for us. Every distortion component, it'll give us at every single frequency. And that's the way that I like to test when I'm designing. I like to test that. I'm also gonna, there's the FFT that function you can get on a computer is also generally superior to what they build into these little cheap scopes. And so next time, maybe we'll test the same amplifier. I'll just do the same amplifier. But next time what we'll do is we'll be using some software and a sound card to run sweeps on the amplifier. That'll be fun. All right, hope you've enjoyed the video.